Okay, welcome students to section 8.3, the method of annihilators. Okay, the method of annihilators. Okay, definition. The general solution a linear non-homogeneous differential equation equal to f of x is of the form y of x equals yc of x plus yp of x. Or yc of x is called the complementary function. And yp of x, oh, sorry, and is the general solution to the homogeneous differential equation P d of y equals 0. And yp of x is a particular solution of the non-homogeneous okay, a technique for obtaining a particular solution. Solution is called the method of undetermined coefficients. Of undetermined coefficients. It is applicable to linear differential equations that satisfy differential equations has constant coefficients. And can be expressed as d y, sorry, differential operator, polynomial, times y is equal to f of x. Number two, there exist differentially differential operator AD of lowest order called the annihilator of f, such that when I multiply AD times f of x, it equals 0. Okay, interesting. Okay, so let's use this. One, determine general system. Two, y double prime minus 9y is equal to 10 e to the 2x. Okay. This is going to be d squared minus 9 of y is equal to 10 e to the 2x. So let's solve, let's get yc, which is just solving for the homogeneous part. Okay, so d squared minus 9y is equal to 0. So we're going to get p of r is equal to d squared minus 9, or sorry, r squared minus 9. So we get r minus 3 and r plus 3. So we can have r1 equaling negative 3. And r2 equaling 3. Okay, and those are both multiplicity 1. Okay, so I know that y of c of x is equal to c1e to the negative 3x plus c2e to the 3x. Okay, now let's look at f of x equaling 10 e to the 2x. Okay, I need a of d times 10 e to the 2x equaling 0. I need some annihilator polynomial there that's going to get rid of e 10 and e to the 2x. Well, I could divide by 10. And that just tells me that AD times e to the 2x is equal to 0. Now let's assume that the particular solution in this case is some constant times e to the 2x. Okay, or yp of x equals some constant times e to the 2x. Okay, where a naught is called the undetermined coefficient. Okay, we don't know what that coefficient is. It is a particular solution though. So we need the coefficient. And we need to figure out what a naught has to be. Okay, well, if we take y prime of px, we get 2a naught e to the 2x. Okay? And I can write this as a differential equation. I can now say that y prime p of x, okay, is equal to 2 times y p of x, right? Because it's just double. Y prime is double what the yp of x is. If I toss that to the other side, I get yp prime p of x is equal or minus 2yp of x is equal to 0. Then I can rewrite this using my polynomial my polynomial operator, differential operator. I can rewrite this now as d minus 2 yp of x is equal to 0. Okay, so this tells me that yp of x was okay, so I get AD, okay, AD times yp of x is equal to 0. So instead of a PD, we're using an AD for the annihilator. Okay. So what I can do now is I can add this to my original differential equation. Okay, I can add this to my original homogeneous differential equation. I could say this thing's gonna annihilate or get rid of the f of x. Okay. And so I'm gonna do d minus 2 times d minus 3 times d plus 3 of y is equal to 0. Now this thing has multiplicity 1. Okay. And I also know that yp of x is equal to a naught e to the 2x. That's the way we set it up. Okay, and we also know that d squared minus 9 of y is equal to 10 e to the 2x. Okay. So now we're gonna take some derivatives here. We're gonna say that y prime of p of x is equal to 2 a naught e to the 2x. and y double prime of p to the x is equal to 4 a naught e to the 2x. Okay, and so y double prime, okay, that's my d squared. Okay, y double prime is d squared. So this is going to be 4 a naught a naught e to the 2x minus 9 minus 9 of y, okay, of y minus 9 of yp, okay, this whole thing of yp. Yp is a naught e to the 2x, because that's, okay. So this was the second derivative minus just 9y is equal to, that was in the original, right? If we look at the original differential equation, okay, it's y double prime. Oops. Okay, it's y double prime minus 9y. So we get that y double prime there, and then it's minus 9y. Okay. Maybe I should have added that step there. Okay, maybe I'll move this down a little bit. That down. And then we'll put in that step of that thing there, d squared minus 9. That converts back to my original differential equation, y double prime minus 9y equals 0. Okay, and this particular solution kind of always goes along for the ride. It's always going to get taken the second derivative times the original function. Okay, but we're saying now that that is equal to 0. Okay, if we have it of this form. Okay, and so this is equal to, sorry, this is equal to not 0. Why I said 0. That's equal to 10 e to the 2x. There we go. That's equal to 10 e to the 2x. And so we can solve for a naught here. This is going to be negative 5 a naught e to the 2x is equal to 10 e to the 2x. Okay, divide by negative 5 e to the 2x, and we get a naught to be negative 2. Okay, so my y of p is equal to negative 2 e to the 2x. Okay, so my general solution here is going to be y of x is equal to my y of c of x plus my y of p of x. Okay, and so y of x is going to be equal to c1 e to the negative 3x plus c2 e to the 3x plus, or I should say minus 2 e to the 2x. That's my solution to that second order non-homogeneous differential equation. Okay. Okay, now for this technique to work, we have some conditions. F of x must be of, of the following forms. Okay, number one. C x to the k e of ax, where k is a real number. Okay, it's actually a natural number. Okay, and k can be 0. Okay, so we could just have e to the ax. Okay, two e x to k e to the ax times sine of bx. 3 c x to k e to the ax cosine of bx, or 4 any sum of any combination of the top three. Any sum of 1 through 3. Okay. Now we can help ourselves out with a little chart here. Okay, we just made kind of an educated guess up here as to what y of p would be. Okay, and we can actually make a chart that tells me exactly what y of p to use given a certain a of d. Okay, so let's create a chart. Okay, if your f of x is a certain thing, then your a of d is going to be of a certain characteristic, a certain form. And that would mean that the y of p that I want to choose, okay, is of a certain form. So let's look at this chart here. Okay, so if f of x is of the form e to the ax, x e to the ax, or any x to the k e to the ax, then my differential operator, my annihilator, basically, that I'm going to end up with is d minus a to the k minus 1 power. Oh, sorry, k plus 1 power. And so if I get x to the first, okay, then that's going to be d minus a squared. But if I get x to the 0 power, okay, which is just e to the ax, then that's going to be d minus a to the first power. Okay. Okay, and so what should I choose for y of p? Well, we need to choose y of p e to the ax times a naught, okay, plus a1 of x plus plus so how many x's I have to the power, okay, then I just keep adding terms. Okay, this is plus a of k x to the k. Now if I don't have an x, then I just end up with a naught e a to the x, which is what we had we used in the last problem. Okay, so we didn't have an x in front of e to the ax, so we just, okay, used e to the ax times a naught. Okay, if I have some sort of polynomial, okay, little a naught, okay, lowercase a naught plus a1 x plus a2 x squared. A plus dot 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 plus a k x to the k, then the annihilator that I'm going to choose is d to the k plus 1. Okay, and then this just becomes a naught plus a 1 x plus a 2 x squared plus dot 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 plus a k x to the k. So you don't have that, we don't have that e. Okay, but in this case, if we look at and we say a in my in the ea to the x, if I just let a be 0, okay, lowercase a be 0, then that will give me kind of the same thing that I have here, okay, underneath, okay, just with various coefficients. So we don't end up with that minus a in this case. We end up with, just d to the k plus 1. Okay, the next one is what happens if I have a cosine bx or a sine bx. What happens if we have a cosine bx or a sine bx? And this ends up being d squared plus b squared. That's the annihilator that I'm going to choose. Okay, to use. Okay, and my particular solution is going to have a naught cosine bx, okay, plus b naught sine bx. Okay, and it doesn't matter if it's cosine or sine because we're gonna have to deal with the fact that we could have either a cosine or a sine in our answer and our particular solution. So we just add them together. Okay. What if we have e to the ax times cosine, kind of combining the first one with cosine bx, or e to the ax sine bx. We take that form, then what do we have? Then we have d squared minus 2ad plus a squared plus b squared. Okay, interesting. So it's basically d minus a quantity squared, okay, plus b squared. Okay, and then what's the particular solution that I'm going to choose to use is e to the ax a naught cosine bx plus b naught sine bx. Okay, and the last variation of this is what happens if we have all three together. If we have x to the k, e to the ax, cosine bx, ax, then what we get is we get e squared minus 2ad plus a squared plus b squared all to the k plus 1 power. We're kind of combining everything. Okay, we're combining the e to the x, which is going to give us a power as d minus a times a power, and then cosine bx and sine bx, that's going to give me the squares. Okay, and then the x is going to give me the raised to the k plus 1 power. What would I use as my particular solution? Well, it's pretty long actually. It's e to the ax, okay, times, okay, a naught cosine bx plus b naught sine bx, so that would be the first one, plus, okay, and then if we had the next term, that would be an x times the same thing. It would be a naught, or sorry, a1 in this case. So however high x goes is however many terms we have here. Okay, a1, if I can do this. Okay, a1, okay, cosine, oops, this is a little more than I wanted. Okay, a1 cosine bx plus a1 sine bx, okay, plus, okay, I'm going to go to the next line, dot, 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 plus x to the nth, a to the k cosine bx plus a to, I'm sorry, it would be b to the k. B to the k, this would be plus b1 sine bx, and then b to the k, b to the k sine bx. Okay, do a dot, 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 dot. Okay, so that kind of tells you what to use. Okay, what's the annihilator we're going to use, and what's the particular solution going to look like. Okay, so it kind of takes a lot of the guesswork out. Okay, let's do another problem here. Okay, problem number 2. Okay, determine 2 d minus 4 times d plus 1 of y is equal to 15 e to the 4x. Okay, so here they're giving it to me in operator form, which is fine. I mean, doesn't matter. Okay, so we first want to solve for the homogeneous equation. So d minus 4 times d plus 1 of y is equal to 0. Okay, so, this is kind of simple. If I have r minus 4 times r plus 1 is equal to 0, that, then I get r equal 4 and r equal -1. We'll do the -1 first. Okay, r equal -1 and r equal 4. Okay, so I know that my y of c is going to be equal to c1 e to the -2 e to the 4x. Okay, so that's the easy part. Okay, now I need to know, well, what's my what's my annihilator gonna be? Well, I have e to the 4x here. I kind of ignore the 15 for right now. But we have e to the 4x. If we go to my chart, that's e to the ax is going to be d minus a to the first power, or just d minus a. So it's going to be d minus 4. Okay, based on this guy here. Okay, we would say f of x is equal to 15e to the 4x. So a of d, what my annihilator is going to be equal to d minus 4. Okay, so I'm going to place that back in. Okay, and I'm going to say that I'm going to have d minus 4 times d minus 4 times d plus 1 of y equal to 0. Okay, because that's going to annihilate. Okay, but what happens in this specific case is I get multiplicity of 2. Okay, I already have a d minus 4. So I end up with multiplicity of 2. So we need 1 degree higher for yp of x. Okay. Okay. Since, okay, if you look at this term up here, C2 e of 4x there we go. C2 e of 4x right here. Okay, that was, I already have an e to the x in my general solution. So if I did another e to the 4x with just a constant in the front, it would just, those constants would add together, and I wouldn't have covered the fact that I could have had an x e to the 4x. We need 1 degree higher for y of p, since C2, okay, since C2 e to the 4x is a part of the general solution, a general homogeneous solution, or just YC. Okay, honestly. YC of x. Okay, it's already part of YC of x. Okay, so we're going to choose our YP of x to be equal to A naught x e to the 4x. Okay. So we need multiplicity too. Okay. Okay, it's already part of the complementary function. Put that in. Okay, so we need to raise it to 1 power higher, which is going to give me that A naught x e to the 4x. Okay, so now let's try to solve for the A naught. Okay. What would be my original differential equation? Well, my original differential equation, they said, was d minus 4 times d plus 1 of y is equal to 0. If I multiply this back out, I would end up with d squared minus 3d minus 4 of y equals 0. And then what would be my differential equation? It would be y double prime minus 3y prime minus 4y is equal to not 0. I keep it's 15 e to the x. I'm sorry. It's 15 e to the 4x. X, 15 e to the 4x. Okay, so I want to figure out, well, I need a y double prime, I need a y prime, and I need the y, and I need it to equal 15 e to the 4x. Okay, so what would be y prime of p would be equal to, do the product rule here. So that's going to get me a e to the 4, or a not e to the 4x plus a 4a not x e to the 4x. Now let's take a second derivative of that. Okay, y double prime of p is going to be equal to, that's the same thing, a, or sorry, 4 a not 4x plus, okay, and then I get this to be the product rule again. That's going to be 4a not e to the 4x. Okay, plus 16 a not x e to the 4x. I could combine those two nicely into 8 a not e to the 4x plus 16 a not x e to the 4x. Okay, so now I'm going to plug this back into my original and solve for a. Okay, so I know that y double prime was 8 a naught e to the 4x plus 16 a naught x e to the 4x minus, that was my y double prime, minus 3 times my y prime, which is okay, which is a naught e to the 4x plus 4a naught x e to the 4x. Okay, and then minus 4 times y p, which is just a naught x. Oops. A naught x e to the 4x. Okay, and that is equal to 15 e to the 4x. Okay. Now let's try to solve for a naught. Okay, so let's distribute this negative 3. I get 8 a naught e to the 4x plus 16 a naught x e to the 4x minus 3 a naught e to the 4x minus 12 a naught x e to the 4x minus 4 a naught x e to the 4x is equal to 15 e to the 4x. Okay, well this 16 and the minus 12 and the minus 4 are all going to cancel out. The 8 a naught and minus 3a naught, that's going to be 5a naught. We get 5a naught e to the 4x, okay, minus, no, just equals 15 e to the 4x. If I divide by 5 e to the 4x, I just get a naught to be equal to 3, which is what I wanted. Okay, so my particular solution, yp of x, is going to be equal to 3x e to the 4x. So I know that my solution to my differential equation is going to be y equals c1 e to the negative x plus c2 e to the 4x plus 3x e to the 4x. And that's my general solution to the non-homogeneous differential equation. Okay. Okay, let's try one more here. Okay. Number 3. Okay, solve the initial value problem. Y double prime with y prime minus 2y is equal to 10 sine x, where y naught is equal to 0, and y prime of 0, or y of 0 is equal to 0, and y prime of 0 is equal to 1. Okay. Okay, so let's first get the general solution, and then we'll get a particular solution. Okay, so we have e squared minus d minus 2 of y is equal to 10 sine x. We're going to find the homogeneous solution first. Okay, let's factor this guy. This is going to become factored e minus 2 and d plus 1, y is equal to 0. Okay. And so we know that basically y of c of x, my complementary function, my complementary function, okay, is going to be equal to, okay, c1 e to the, well, here, we'll say that r is equal to 2 and r is equal to negative 1. Okay, and so c1 e to the 1x, just negative x, 2 e to the 2x. So that's my complementary function. Now let's look at what my annihilator should be. Okay, I just have a sine x. So my annihilator, AD, should just be equal to B. Well, B would be the number in front of the X, and that's just 1. So it's going to be D squared plus 1 squared, which is just D squared plus 1. Okay, so that's my annihilator. Okay, so I have D squared plus 1 times, okay, D minus 2 times D plus 1. Okay, that's going to end up equaling 0, because I'm including my annihilator there. And I only have multiplicity 1. I just need to plug this into check to make sure I don't have any multiplicities. And I only have multiplicity 1 on that D squared plus 1. So that's nice. Okay. So we're going to use yp of x is equal to, okay, for sine x, we can go back to our chart. Okay, for sine of x, we're just going to be a naught cosine bx, and in this case, b is 1. B naught sine of bx. So it's just going to be a naught cosine x, b naught sine x. A naught cosine x, b naught cosine x plus b naught sine x. Okay. So now I want to take successive derivatives of this. Okay, because I want to plug this back into my original differential equation. Okay, and I know it was a second order differential equation. So we can solve for a naught and b naught this time. We have 2 things to solve for. Okay. So y prime of x is going to equal a naught. The derivative of cosine is negative sine, so that's sine x plus the derivative of sine is cosine x. Okay, and then y double prime p of x, we're just going to kind of be negative a naught cosine x minus b naught sine x. Okay. Okay, so let's plug this into our original differential equation. What was that? Y double prime minus y prime minus 2y equals 10 sine x. And so I get, for y double prime, I get a naught cosine x plus b, whoops, I need y double prime, not y. This is negative a naught cosine x minus b naught sine x. Okay, minus y prime, which is the row above it, negative a naught sine x plus b naught cosine x minus 2 times the original, which is a naught cosine x plus b naught sine x is equal to 10 sine x. Okay, so let's distribute. Okay. Okay, so I've got negative a naught cosine x minus b naught sine x plus a naught sine x minus b naught cosine x minus 2 a naught cosine x minus 2 b naught sine x is equal to 10 sine x. Okay. Okay, so the only 2 things that combine here are these 2 guys, a naught cosine x and b naught sine x. Okay, and so that's going to be negative 3 and negative 3. Yeah, negative 3 a naught cosine x. Okay. I'm gonna put the cosine x, the cosine x next to it, minus b naught cosine x. Okay, now let's deal with the signs. This is gonna be -3 b naught sine x plus a naught sine x. Okay. Oh, looks good. Okay, is equal to 10 sine x. And what I'm going to do is I'm going to add a cosine x onto this. I'm going to go plus 0 cosine x. So we've got cosines and sines. Okay. I'm going to factor out a cosine here, factor out a cosine there, and have factor out a sine there. What I end up with is I end up with -3 a naught minus b naught times cosine x. Okay, plus I'm gonna factor out the sine x, but I'm gonna rearrange the terms. A naught minus 3 b naught equals equals or times sine x is equal to, I'm gonna rearrange these as well. I'm gonna go 0 cosine x plus 10 sine x. And now I can kind of relate these one to one and create a system of equations. That is going to equal that, and that is going to equal that coefficient. I can look at the coefficients, and this tells me that -3 a naught minus b naught is equal to 0, and a minus 3 b naught is equal to 10. Okay, so this is very simple system of equations. I could multiply everything through by 3 if I wanted to on the bottom. Okay, so this would be -3 a naught minus b naught equals 0. I could also use substitution if I wanted to. There's a kind of a bunch of things that I could do pretty easily. If I did 3 a naught minus 9 b naught is equal to -30. No, positive 30. I'm sorry. Positive 30. One equals 30. Okay, so now let's add these together. I get rid of the a naughts. I get -10 b naught is equal to 30. So divide by -10, and I get b naught is equal to -3. So what was a naught? Well, from here, we could plug this back in here, and we would say that a naught minus 3 times -3 is equal to 10. This is a naught plus 9 equals 10, so a naught is equal to 1. Okay, so what's my particular solution? It would be, it was a naught cosine x b naught plus b naught sine x, a naught cosine x plus b naught sine x. So that would be equal to just 1 cosine x, so that's cosine x, and this is -3 sine x. So that's yp of x. What was our yc of x again? Yc of x from above was c1 e to the negative x plus c2 e to the 2x. And so our general solution is going to be putting these two together. Y of x is equal to c1 e to the negative x plus c2 e to the 2x plus cosine x minus 3 sine x. And that's my solution. Okay. Okay, so that was 8.3. And I'll see you in the next section.